Swayam Prabha. Digital India. Educated India.
Now let's proceed with mesh analysis of circuits with resistors and independent voltage sources. I have put down the same circuit that I considered earlier, and I will identify the three mesh currents. Okay, let me call this mesh number 1. So this is current I1, and this is I2, and this is I3. Okay, and as we saw, the current in this branch is I1, this is I2, and this is I3, whereas the current here is I1 minus I3, current over there is I2 minus I3, and current over there is I1 minus I2. Okay, so what I'll do is I'll write Kirchhoff's voltage law equations around each mesh. So let me take mesh number 1. Okay, and let's say I will go in the same direction as the mesh current, that is clockwise direction, and I will write the voltage drops across all resistances to be equal to the voltage rise across the voltage source in the loop. Okay, so this is the way I choose to write it. Just like for nodal analysis, while writing Kirchhoff's current law equations, I wrote the sum of all currents going out of a node through conductances equals the sum of independent currents being injected into the node. Here also I will write sum of voltage drops while traversing the mesh to be equal to the voltage rise due to the independent voltage source in the mesh. Okay, so if I do that, what will I get? The voltage drop across R11 is simply I1 times R11, and the voltage drop across R13 is its current I1 minus I3 times R13, and the voltage drop across R12 is I1 minus I2, that is the current through R12, times R12, and that will be equal to the rise of voltage V1. Okay, now this is the Kirchhoff's voltage law equation around this loop. Okay, we have implicitly used Kirchhoff's current law because this current here, that is the mesh current I1, the current here is I3, so we wrote the current in R13 to be I1 minus I3. That is basically Kirchhoff's current law applied at this node. Okay, so we have implicitly used Kirchhoff's current law also while writing this, and this is exactly the same thing that we did with nodal analysis. We were writing Kirchhoff's current law equations, but we were implicitly using Kirchhoff's voltage law when we wrote down that the voltage across each branch is difference between two node voltages. So that's for mesh number 1, and if I group terms containing the same mesh current, I will have I1 times R11 plus R12 plus R13 minus I2 times R12 minus I3 times R13 to be equal to V1. Okay, what I have done is I have collected the coefficients of the mesh currents. Now the pattern must be very obvious to you. What is the coefficient of a given mesh current? I am writing the equation for mesh number 1, and I1 is the current for mesh number 1. So then the coefficient of I1 will be the sum of all resistances in that mesh. Okay, so I1 belongs to mesh 1, so the coefficient of I1 will be sum of all resistances in mesh number 1 when you are writing the equation for mesh number 1. And what is this R12? You can see that that is the boundary between mesh 1 and mesh 2, or R12 belongs to both mesh 1 and mesh 2. So the coefficient of I2 will be negative of the resistance common to mesh 1 and mesh 2. Okay, and finally R13, what is that? That's the resistance common to mesh 1 and mesh 3, so that's the coefficient of I3, that is negative of the resistance common to mesh number 1 and mesh number 3. Okay, so what's the summary here? If you write the Kirchhoff's voltage law equation around a particular mesh, it will have terms containing all the mesh currents. Okay, now the coefficient of the mesh current for that mesh would be the sum of all resistances in the mesh, and the coefficient of the other mesh currents would be the negative of resistance which is common to this mesh and that particular mesh. Okay, so again the pattern is exactly the same as nodal analysis, right? So let's write the equation for all meshes. Mesh number 1, we have already done that. It is I1 R11 plus R12 plus R13 minus I2 minus I2 R12 minus I3 R13 equals V1. Okay, let's do it for mesh 2. Then again we have the voltage drops, right? And I'll take all the voltage drops as I go in the clockwise direction. So if I take the voltage drop in that direction, that is like this, you see that it is I2 minus I1 times R12. Okay, in this direction it was I1 minus I2 times R12. In the opposite direction it is I2 minus I1 times R12. So I'll have I2 minus I1 times R12. Okay, and I have R23 here. The current through that is I2 minus I3. So I2 minus I3 times R23. Remember, I am going around this mesh and I am considering voltage drops in that direction. Okay, the voltage that drops as I traverse the loop in clockwise direction. So that's I2 minus I3 times R23 plus I2 times R22, because the current through R22 is just I2, and that is equal to the voltage rise as I go in the clockwise direction. Okay, so when I go from here to there, the voltage actually falls by V2, or the voltage rises by minus V2. So this is equal to minus V2. Okay, and again I collect all the coefficients. I'll have minus I1 times R12 plus I2 times R12 plus R22 plus R23 minus I3 times R23 to be equal to minus V2. Okay, so this is again something that follows the same pattern. For mesh number 2, the coefficient of I2 will be sum of all resistances in the mesh. Coefficient of I1 will be the negative of resistance common to mesh 1 and 2. Coefficient of I3 will be negative of the resistance common to meshes 2 and 3. And just for completeness, I will do it fully for mesh number 3 as well. And you see that going in the clockwise direction, again we have the voltage drop this way is I3 minus I2 times R13. The voltage drop that way is I3 R33, and the voltage drop this way is I3 minus I2 times R23. So if I are writing the equation for mesh number 3, the current I3 will have positive coefficients. Okay, that's something to keep in mind. So I have I3 minus I2 times R13 plus I3 R33 plus I3 minus I2 R23 to be equal to 0. There is no independent voltage source in this mesh. Okay, again collecting the coefficients, I have minus I1 R13 minus I2 R23 plus R13 plus R23 plus R33 times I3 to be equal to 0. Okay. Now I'll put this in a matrix form, which is convenient. I have this times the mesh current variables I1, I2, I3 being equal to the independent sources, the source vector, which is V1 minus V2 and 0 for our particular circuit. Okay, so this is of the form the resistance matrix times the vector of unknowns, the vector of mesh currents, to be equal to the vector of independent voltage sources. Okay. The three rows are equations for the three meshes, and you see exactly similar properties to what we had when we had nodal analysis with resistors and independent current sources. We have a symmetric matrix, symmetric resistance matrix, and the diagonal elements correspond to total resistance in the mesh, and the off diagonal, it's the negative of resistance common to corresponding meshes. Okay, so now you can by matrix inversion solve for the unknown mesh currents I, and from those currents you can get the individual branch currents. Okay, for instance, we have already identified that the current through R11 is I1, R22 is I2, and R33 is I3. Similarly, the current through R13 is I1 minus I3, R12 is I1 minus I2, and R23 is I2 minus I3. So from the mesh currents you identify all the branch currents, and from that you can identify all the branch voltages. Of course, for voltage sources the branch voltage is independent of the current, but in general you get the branch voltages from the currents that you have calculated and the IV relationships of the element. Okay. So you first solve for mesh currents. The mesh current vector equals the inverse of the resistance matrix times the vector of sources, and you find all the branch currents from the mesh currents, and finally find all the branch voltages from mesh currents and element relationships. Okay, so with this you have the complete solution to the circuit. Okay.